real deal on stage and talk with somebody that's actually doing this for real. And where is he? I'm gonna bring Matei to the stage. Paging Matei.
Hey,
There he is.
how's it going?
Dude, it is great to have you here, man. I am so excited. This is like something that, of course, it's always a pleasure talking to you. And as I mentioned when you came on the podcast, for I think the ML world and the MLOps world, you're like the DJ Khaled of our industry because you just keep dropping hits and hits. I mean, before, let's just give it in case, and for like the two people that do not know you, you created Spark. You were co-creators of Spark. You also had your hand in MLflow that everyone knows and loves and is starting to play around. MLflow now supports LLMs, which maybe you're going to talk about, maybe not, but we should talk about that later. And then since we talked last, man, you dropped Dolly. So, I mean, wow. And then you've got your name all over all kinds of cool papers. Frugal GPT. If anyone has not read that paper, that is incredible. I really love that you're still keeping your roots in the academia and putting out papers. And so, man, last thing I want to announce to everyone before we get started, and I'm going to let you take over and drop some wisdom on us. In 2 weeks, on June 26th in San Francisco, you and we're going to meet face to face. We're going to be in person at the LLM Avalanche meetup that we are both doing. And that is, it's like the sound check, or it's gearing up for the Data and AI Summit that you all are putting on. And so I'm super excited for that. If anyone is in San Francisco for June 26th, let us know. I'm going to drop a link to that in the chat, and I'm going to hand it over to you, Matei, man. It's great to have you here.
All right, thanks a lot. I'm just excited to be here. Let me share. Ooh.
Now the fun part starts. Now
this requires AGI to figure out.
This is not your regular Zoom call, man.
Yeah.
All right.
Okay. Do you see my slide?
I do. I see it. Yep.
Okay. Perfect. All right. So I'm going to talk about this emerging area of LLM Ops and some of the things that I'm seeing in industry at Databricks, both building our internal LLM applications, which we have, quite a few of, and, helping, our customers with them. And I'll also talk about some research that I've been doing at Stanford, even kind of before ChatGPT became really popular, on using LLMs more reliably. That is also, I think, relevant to this field. So it'll be sort of a tour of a bunch of things, I'm also going to list a bunch of stuff that I'm not working on at all, but that I think is cool. And hopefully it gives you, a little bit of a perspective of how to approach this problem. Okay, so large language models are super amazing. They can, generate text as very fluent, often very grounded in reality. You can do a lot of cool applications with them, all the way from the traditional, few shot classification type of stuff to new things like chatbots, where you can ask questions. They know about all kinds of recent research and stuff like that. They can even do programming. So very cool. But if you look at these answers a little bit more closely, there are actually, a bunch of problems. So for example, this first one, we asked ChatGPT when was Stanford University founded, and it says 1891, but that's actually wrong. That's just when the first class came in, but the university was founded earlier. ColBERT, this is a model that my research group developed, so we were super excited that ChatGPT knew something about it, but it says it was developed by Salesforce Research, which it wasn't. It was developed by us at Stanford. And finally, this code here, you can't see, it's not showing all the code, but it's saying to parallelize this code, you should use thread pool executor. But the problem with the code was actually that it's some kind of serial algorithm. So you need to change the algorithm. So you can't just throw in thread pool executor. So there are definitely challenges with the quality of responses in LLMs, especially if you want a production-grade app. And on top of that, there are also other operational challenges with cost, performance, privacy, and just the need to update your model and your application. So here are like some examples of things that can go wrong. Of course, these models are expensive to run early on. They used to go down some of the time because of the load. Another interesting issue that people have been talking about is prompt drift, which is the models are changing, over time as they're being trained, and they might get worse at like some tasks they could do before. Now they're worse at it. And then there are also issues with timeliness and with privacy that affect a real app. So even today, if you ask, all these OpenAI models about, events past 2021, they don't know. So, and obviously it's expensive to update them. Otherwise, they would have updated them by now. And if you have an application with privacy, with the emerging sort of rules around privacy, you might also run into issues there where a user wants to remove their data. So, for example, ChatGPT seems to know something about where Bill Gates lives, but if Bill Gates was a European or a Californian, he could ask them to remove that data about him, and then it would have to forget this information. So the question is, how can we make LLM apps reliable? This is this area that people are calling LLM Ops, and I'm going to talk about like three things in this area. The first one is, how do we extend what we currently do in MLOps to work well for generative AI? And I'll talk about what we're doing in MLflow specifically based on our experience. The second is new programming models for these kind of applications, which is one of the things I've been doing at Stanford. And then I'll talk a little bit about other emerging tools too. Okay, so let's start with the basics. So I really think that for anything you're doing with language models, even though it's a really cool new kind of application, if you want it to work very reliably, you want a way to improve it, you need to start with the basics, and these are the same as in MLOps the way it normally was. So one of the most basic things you need is a way to swap and compare different models or even pipelines of models, because a lot of this is done using chaining now, for an application, and just say how are they doing at different stages, how do they compare on different metrics. So you should set up your development infrastructure to support this simple kind of comparison task. Second thing you need is to track and evaluate outputs, and have this historical database of what happened so that you can kind of search. You need a way to deploy pipelines reliably and see what's happening. And you need a way to monitor these deployed applications and analyze the data once they're actually out to see what's happening with them over time. So we're trying, we're basically implementing all of these in the MLflow open source project. And then the part that ties with data, we're also integrating into just Databricks as a platform. If you want to have kind of a consistent platform across data engineering and ML engineering, we're designing it so it's very easy to do both of these things. So let's start with the first one, swapping and comparing language models. So in MLflow, if you're not super familiar with it, one of the key concepts there is this model abstraction that can wrap a model. So the rest of your code doesn't need to know how it's implemented. You don't need to know, what framework is it using? Is it a local model or something I'm calling over the network like OpenAI? Is it, a single thing or is it a pipeline actually of multiple steps? You just basically have this function. For example, a function from string to string could be a call to OpenAI or a local model or some kind of pipeline. And we've created integrations with a lot of the popular LLM tools to let you manage them as models in there. And the same thing with pipelines. Specifically, we've been focusing on LangChain for that. So you can easily wrap all these things into these model objects, and then in your application you can swap them. In your evaluation code you can compare different ones. You could imagine like routing some percent of traffic to one versus the other, and so on. So then you can just call these general functions on each one. So that's very basic but important, and we're seeing this come up a lot as people want to try different options in this space. A second thing that we're doing for the experiment tracking is extending what we call auto logging in MLflow. So in MLflow, the idea is, you develop your machine learning code, and we have some lightweight calls you can make that cause MLflow to record what's happening, wrap it into these kind of generic formats like the model I talked about, and make it easy to evaluate and compare and track results over time. So one of these is, you can just do MLflow.start run, and then you can train models and log them and so on. So we've extended this auto logging for OpenAI, so you can remember basically a prompt and other parameters you used in OpenAI and wrap that up and call it later with model.predict. And we've also extended it with LangChain, so you can set up a chain with local models or remote models and save it, and again, load it later and call stuff about it. And once you've run these, the other thing we've done is in the UI, we've created a new view in the UI that works well for evaluating long form like generative outputs, like these texts from these models. So basically, you can run all these models on some evaluation data set, some questions or whatever, some input text, and then you can see for each one side by side, you can see what they each producing. We're also going to extend this so you can actually add ratings like right here, or import ratings from a third-party labeling service. So you can compare all of them. And of course, once you've saved these models, you can also evaluate them programmatically. We have this function MLflow that evaluate with a lot of common metrics people want to run. And we've put in a lot of the metrics you want for LLM applications, like the Rouge metrics for summarization, and various other ones, some metrics on toxicity, various things like that. You can also easily extend this to have your own. So that's basically like working with the models themselves. And then, of course, you also want to deploy the models and check what's happening after. And the way MLflow works, you can deploy a model to a variety of different serving layers. We want to make it portable across them. So you can pick your favorite one here. And once deployed, you can get these predictions out of it. And this is like one of the areas where on Databricks specifically, we've integrated this very closely with what you do for data engineering. Like basically, as your model runs, you just get a table that's automatically created, and you can run alerts on the table. You can basically have a SQL statement and say, alert me if whatever this SQL statement ever returns, true or something like that. So it's easy to do that, but you can use whatever deployment tool you want with this stuff. Just a little bit more on some of the things we're doing with this at Databricks. We've also released some reference applications, like for example, how to do a customer support bot that includes a vector database, language model, and the ability to say, it doesn't know about certain topics and so on. So some kind of filtering. And we've also released this free course on edX on LLMs application to production that covers, what we've been seeing at different stages of this workflow, not just LLMs themselves, but all the peripheral things like monitoring, searching, vector databases, chains, and stuff like that. So that's kind of the basics of MLOps, and they will definitely help you like get from a demo, which is usually easy to make with these LLM tools, to something that like works reliably, 80, 90, hopefully eventually 99% of the time or more. But it's still, it's still a lot of work to make these happen. So I also wanted to talk a little bit about what the future of programming with these models could look like. And this is one of the projects that my grad students have been doing at Stanford. It's called DSP, or Demonstrate, Search, Predict. So today, if you look at not just LLMs, but foundation models in general, these pre-trained models that on large data sets, there are so many different tools and techniques you can use. Just for language models, there are different ways to use them. There's instruction, prompting, chain of thought, agents, fine-tuning, and so on. And in addition to language models, there are different retrieval models, your favorite vector index and database, task-specific models, and maybe models for other things as well, like vision and speech that you want to combine. And most people want to build these into pipelines. So we're seeing that, you've seen it if you've used LangChain, or probably it's just a very natural way for you to work with these. So the idea is you break down your problems and delegate smaller subtasks to the models. And I'm showing a couple pipelines from the research literature on the right that are, kind of did this by hand. So in principle, it sounds great that you can just make a pipeline. But in practice, it's actually pretty hard to connect all these pieces and then to optimize the whole pipeline. If you want to get from like whatever default accuracy it has as you hook everything up to increase your accuracy and say eliminate like the some type of bad output it's producing or something like that, you've just got all these models sitting there, maybe with prompts or with like some Python code to glue them together, and it's quite hard to fix that. And every change you make to the pipeline affects everything in it, all the other models. And for example, if you want to, if you were training one of the models or fine tuning it to deal with like whatever input format you're going to give it from above, you'll have to retrain it if you change what you're doing above. So we want developers to be able to step away from this and just think about their system design and components, not about gluing and optimizing all these stages together. So that's what we're trying to do in this programming model, DSP, or Demonstrate, Search, Predict. So DSP is a declarative programming model for these pipelines. Basically, think of it a little bit like PyTorch, how in PyTorch you can hook together layers that are different, operations, and pass, data in the form of tensors between them. In DSP, the layers are actually different foundation models, like language models or retrievers or potentially other things, a calculator, maybe some other, string-to-string function. And then the stuff you're passing between them is text objects, it's not tensors. So there are three types of functions in DSP, or primitives you can use on your program. There's demonstrate, which is how you tell it what to do. This can be basically providing some training data or other ways to specify constraints. There's search, which is breaking down problems and looking up useful information. This is where something like a vector database would come in. And then there's predict, which is different strategies for using the information you pulled out, checking the quality, asking, is this really the right answer, and so on. And you set up your program, but once you set up the different steps in it, you delegate to the DSP runtime to figure out how to implement each component. And it sees the whole pipeline and it tries all these techniques I had on the previous slide, the few shot prompting, chain of thought, different ways of selecting data for each step to automatically tune the whole pipeline. So you don't have to do that yourself. So let's just show a little bit of an example here. This is from this research project we did called Baleen, which is a system that can answer complicated questions using multiple searches over text documents. So for example, over Wikipedia. So one example of the kind of question you could ask was, when was the creator of Hadoop given an award? So Hadoop is a piece of software that was designed by Doug Cutting, and then Doug Cutting got this O'Reilly Award in 2015. But to answer this question, if I gave you this question as a person, you'd have to do a bunch of research, a bunch of searches over Wikipedia or whatever to figure this all out. So this is how you write that in DSP, and hopefully you see it's very simple. So basically you have this example. The example is what holds our state. You can have different fields on it. And you can say, hey, you can have a maximum number of searches or hops it's doing. And what you can do is you can say, hey, first generate a question from this example, like some query that I want to run on my search engine. For example, who was the creator of Hadoop? And then search for that and take the top 3 examples and stick them in this array called passages. And next, generate a summary of everything I've read so far in light of the question and append that to the context. So that's the strategy. Just keep doing these searches. And finally, once you've done this many hops, generate an answer. So it seems a little bit crazy. By the way, these things, the question, the answer, and so on, think of them a little bit like prompts. So it seems a little bit crazy that this would just work out of the box. But if you set up the prompts, it can work sort of okay, not all the time, but a bunch of the time. Just an aside on how to set this up, we actually make the prompts somewhat declarative. So basically you just say, for each step, I'm going to have these inputs like a context and a question here. There's a text description, and then I'm looking for an answer, which is a short sentence. But the DSP framework can figure out how to actually word the prompt to make it give you this. And this is one of the cool things that lets you, evolve your program and optimize it over time. So if you just ran this program, DSP would generate a prompt that looks like this, as it's going along. So let's imagine it did the searches correctly and it found some stuff. It would have these passages here. What is Hadoop? Who was it created by? Whatever. And it uses these items, like it says, hey, I'm looking for a short sentence. So it says answer with a short sentence, right? And it even automatically does chain of thought. It says, hey, fill in this stuff. So this is kind of the prompt it does, and the part in green is what the model fills in. And, in this case, you get the right answer. But this is like basically zero shot. I prompted everything, but it probably won't work all the time. Let's say it only works like 30% of the time or something. How do I make this program better? So this is where you can feed DSP additional data, and it will automatically tune the program to make it work. So one of the things you can give it, and this is this function called DSP compile, you can give it a bunch of like labeled examples of a question like this and the final answer. You don't even have to show it the searches it should do. And DSP is going to like try running each of them multiple times and figure out if it can create a path, like get a path that actually, basically do some searches and actually give you the right answer, because it just knows the right answer for each one. And for the ones where it does, it will use them as few-shot examples in your prompt. So for example, to teach your model, like let's say the final call here is to something like OpenAI, to teach it how to use this kind of context and question and rationale, we gave it this one, but maybe we have an example from the training data where we found that we could answer something. There was this question about which award did the first book of Gary Zukav receive, and we did these searches and we found some stuff. So we automatically found an example that we can put in there, or maybe multiple examples, and we've just gone from instructions alone to few-shot prompting, which works a lot better. And the other thing that it can do here, if you've got enough examples, it can actually fine-tune a supervised model for each part. So instead of trying to do it with chain of thought and so on, you can train a model that's good at answering these kinds of like trivia questions or at generating the searches for them, which works in a similar way. So that's the idea here. We want to separate the your specification of your pipeline from the optimization and to work on them separately. So what this gives you is a great way to do iterative development. It's super easy to get started, and it does something out of the box with instructions, which is probably what you would have done on yourself. It's modular because it unties the system design from prompting and fine-tuning. You can, as we update the DSP software, those parts get better and you don't have to rewrite your whole program. It also enables optimization, because as we make new releases of the DSP compiler, for example, it benefits all the programs. And another really cool thing is that it actually works really well in practice. We've been evaluating this on a lot of research tasks, especially these knowledge-intensive tasks that require looking up information. And compared to other few-shot methods, where you don't tune on like millions of examples, this is basically competitive with all of them, and it's this very simple interface. So in this plot, it's showing a couple of different data sets, and all of these things here are different implementations with engines, and you can see the scores here on different data sets. And the score with DSP, with the same number of examples, I think it's like 10 or 20 examples, is better than all of them in this case, because it automatically searches for how to optimize this. So this is DSP itself. I'll skip this one, but another thing we can do is even feed in unlabeled examples and basically use those to train a cheap model that does the same thing our expensive model does, and to get basically even better performance after you deploy. So yeah, so these are a couple of things, but there's quite a bit more in the LLM Ops space that you should look at. One cool thing is constrained generation. There's this project LMQL, and there's also guardrails and JSON former that force the model to output stuff in a specific syntax that really helps in some applications. Dimitrios mentioned Frugal GPT, which is something we've been developing that can combine multiple models and route queries to them, or combine the results from several models to get better cost performance, like the same, better performance than GPT-4, and even lower cost while achieving that performance. And then there are all kinds of ideas for reasoning, post-processing, filtering stuff that further improve quality. And definitely, if you want to learn more about these, I do encourage you to check out the Data AI Summit, which is like free to view online, and to check out the LLM Avalanche meetup that we're organizing as well. Cool. All right. So I can't hear you for some reason, but let's see if I can fix.
Yeah, that was on my side. And
okay, there we go.
For anyone who came to the first one of these knows that I spent the first 10 minutes talking on mute to myself.
Oh no.
Yeah. And yeah, having a blast. And so I'm waiting for some questions to come through in the chat, because there is a bit of a lag between when we talk right now.
Yeah, makes sense.
People ask questions, but one has already come through, and it's about the latency, and it's asking, do these searches take a lot of time, from Joel Alexander?
Yeah, great question. So it depends a lot on what you use to search. So in DSP, we actually used our own search index, which is called ColBERT over Wikipedia. And so the search is very fast. It's basically maybe tens of milliseconds for each search. It's comparable to the cost of calling the model. So it doesn't have to be. It depends on your setting. If you called out to Bing or Google search, it would be slower.
Mm-hmm. Yeah, that makes sense. That makes sense. And while we're waiting for more questions to come through the chat, I just want to bring up that there is a whole meetup going on in Amsterdam right now, and we've got a live feed of them. And so I'm just going to let somebody jump on screen. Look at that. So they don't know they're on live yet. And now they're going to get it about 20 seconds later. So we're going to take them off before they even realize that they're on. They get to do the, yeah, we're on, we're live.
That's cool.
I'm also going to grab... Oh man, this is great. So we've got Chip coming up next, but before I bring her on, there is a question that's coming through. So DSP is better than DSP better than GPT-4? Is this a correct assumption?
So it depends on the task, but for the tasks we were doing, which are these complicated knowledge tasks, like this Wikipedia one, it's definitely better. Yeah, out of the box, GPT-4 won't do that if you just ask it the question. Of course, you can use GPT-4 as the language model in DSP, so you can kind of benefit from everything it's doing. If you use a better language model, the whole program will do better. But the combining search plus some strategy, I didn't show it, but it can also do things like take a majority vote across answers and stuff like that. Does do better than just the language model alone.
Oh, that's awesome. So the stream just hit the chat because the chat blew up. Now there's so many questions, man. I got to actually point to them and figure out what the best one is. So are there any downsides to using DSP versus alternatives?
Yeah, I mean, so definitely it depends what alternative, but definitely this idea of breaking down your application into many steps will add cost and latency as you run each step. So again, in DSP, the hope is that there you can optimize it, or the most important thing is to get the right quality. But yeah, you can. It will add some cost. Although, so when we started DSP, no one was using chaining at all. So everyone was worried, like, where it's some cost. But now if you use something like LangChain or agents, it's very similar cost. So you can think of DSP as a way to like take that programming model, but try to figure out how to auto optimize stuff in the background.
All right, I got one last one for you, and then we're gonna bring Chip on, and we'll all have a little chat before she gives her presentation. Question for Matei: how does DSP evaluate its optimizations? Does it do them before deployment or even during execution?
Yeah, great question. Yeah, the stuff I showed, the DSP.compile stuff is all before deployment. So there's nothing like online. And you can give it, you can give it some examples where you know the right answer. We're also working on other ways of doing it where you can give it just other metrics or things, you tell it avoid this, this situation. So it's all offline, and then you deploy, and you can collect more data and pass that back in.
Oh, killer, man. So I knew it was going to be great. I did not realize it was going to be so good. You do not disappoint.